And where is the class node? There it is. Okay. All right. So first up is the voltage divider bias. The reason we choose voltage divider bias and the reason why it's one of the most popular ones is that we can bias both the base and the collector with one single supply. Okay, we don't need two separate power supplies. One single supply is sufficient to bias both base and the collector, meaning the input and the output. Okay, so in a voltage divider bias, you have two resistors, R1 and R2, that form a voltage divider network, and you have a RC and RE, collector and emitter resistor. So this is also known as a four resistor bias circuit. In fact, in our book, the Jaeger book that you're using, this is referred to as a four resistor bias. So I will note this down here. And of course, voltage divider because it forms a voltage divider network from R1 and R2. The AC input is typically applied at the base. V out is from the collector and is measured with respect to the ground line. Okay. Now, if we isolate the circuit and cut it in half, let's just take the input side. R1, R2 plus VCC, and then you have the transistor plus VCC. And then, of course, the output of this network goes as input into the base. Now, we are only talking about the DC voltages, right? Biasing is the external constraint placed on the device, right, to fix the operating point. So in this case, if we analyze this, we want the circuit to look like this. Meaning a single voltage source at the base and a single resistor going into the base, RB. Right? So the question is, we need to convert this voltage divider network into RB and VBB. So the way we do that is by finding the Thevenin equivalent network of R1 and R2 as seen by the base and emitter right here. Okay, and so we'll split up the circuit into 2 points, A and B. And we'll then determine the Thevenin equivalent network as seen by the transistor. And so if I was to redraw the circuit, I would say VCC being applied, R1 and R2. And these are my points A and B. Again, I'm simply redrawing the circuit. I'm not changing anything else, okay? This is redrawn like this. That's all it is. So when I redraw this and I want to find the Thevenin voltage and the Thevenin resistance between A and B, well, we go back to circuits 113 or the beginning of this class. We can find VAB as VTH, the Thevenin voltage, which in this case, because it's a voltage divider network, simply be VCC. VCC times R2 over R1 plus R2. And then RAB, the single resistor, would be RTH, the Thevenin resistance. And it would simply be R1 in parallel with R2. So product of the two divided by the sum of the two. right? You want to find Thevenin resistance, then you short or replace all the voltage sources with a short circuit, and you replace the current source with an open circuit. In this case, we have one voltage source VCC, replace it with a short, you get R1 in parallel with R2. So now VAB, of course, is your VBB, and RB is the base, single base resistor RB. Okay. So again, VCC being applied between R1 and R2, we can obtain the voltage across R2. That is our VBB. Okay. So once we have that, we are now ready to apply KVL on both sides of the input and the output. Okay. Now the goal here is to obtain an expression for the output current IC. Okay, the goal is to obtain an expression for the output current IC. And we can apply KVL on the input side, we can apply KVL on the output side. Either ways, which one works? In this case, the input side works. And so if I apply KVL for the input loop, I obtain minus VBB plus VRB plus the base emitter voltage drop plus the emitter resistor voltage equal to 0. Okay, equal to 0. Now, of course, we can describe IE and IB in terms of IC, right? That's why the input side KVL works. So if we replace these and rearrange the terms, I want to get IB on one side. So VRB is IB times RB. And I'm going to keep VRE as it is. And VRE on this side gives me IE times RE. Take the others on the other side, and I would get VBB minus VBE. Okay. Now, IE is IB times beta plus 1. And so I would replace that and obtain IB times RB plus beta plus 1 times IB. And then this is VBB. Yes, times RE. Thank you. Times IB times RE is equal to VBB minus VBE. And then we take IB outside. And we obtain RB plus beta plus 1 times RE VBB minus VBE. I'm going to take everything else except for IB on the other side, and I will replace IB with IC over beta. So IB is replaced with IC over beta, and this becomes VBB minus VBE divided by RB plus beta plus 1 times RE. Now, here's the second significant advantage. In the previous slide or last class, I showed you there's a fixed bias, there's an emitter bias, and then there's a voltage divider bias configurations. The reason we prefer voltage divider bias is so that we can obtain a circuit where the output collector current is almost independent of the transistor beta. Now think about this. You are designing an amplifier, and in this case, it's going to be a common emitter CE amplifier. You're designing this and you want to sell this amplifier, right? in the consumer market. You will source your transistors from manufacturers, and you buy hundreds of thousands of transistors, millions of transistors. No two transistors will have the exact same beta. Even if it's the exact same model, there will be a variation in the beta, right? So you want a circuit where you can plug in any transistor of your choice and will still work the same. That means designing a circuit where the output collector current does not fluctuate with respect to the beta. So if you plug in a transistor with a beta of 100, then the same circuit should work for a beta of 125. And that's where the advantage lies with the voltage divider biasing network. So now that we have IC here, we want to rearrange the terms and we want to minimize the effect of the transistor beta as much as possible. So we take beta on the other side. And multiply and divide the denominator and numerator with beta both. And so we have VBB minus VBE. This becomes RB over beta. And this becomes beta plus 1 over beta times RE. Beta is typically larger than 100. It's a large value. In any case, it's going to be much larger than 1. So we can safely ignore that expression. Beta plus 1 over beta is almost unity. So we approximate, and that is gone. And so VBB minus VBE divided by RB over beta plus RE. So now we have a single value of beta, but if we choose RB over beta to be much less than RE, then our IC is approximately equal to VBB minus VBE over RE. There will be a slight variation. Of course, we cannot completely neglect that term, but we can minimize the effect. Okay, that is the whole point. Also, we cannot want RB to be very, very small. Okay, there is a limit on RB being very small. We want to choose R2 value such that I'm going to have to rush things along, that IR2, the current flowing through R2, is approximately equal to 10 times IB. Okay, 10 times IB. Now, KVL for the output is rather straightforward. We have minus VRE minus VCE minus VRC plus VCC is equal to 0. And so I can write my output VCE plus VRE is equal to VCC minus VRC. Collector voltage is VCC minus ICRC. Okay. Now, moving on to CE amplifier. There is a derivation where we can prove that the gain of this common emitter amplifier is minus RC over RE. This is all mentioned in your lab, the pre-lab. In the pre-lab, you are given the value of RC as 4.7 kilo ohms. You're asked to find a gain of at least 2, and you need to choose a value of RE to provide that gain. So if RC is 4.7K, then you need to choose RE to be no more than 2.2K. These are the resistors in your lab kits. Cannot be more than that. Also, in the lab, we went up to 10 volts for VCE. You can extrapolate that to go up to 14, 16, or even 20 volts, which will be fine. Okay. We are going to do load line analysis when we are designing. We are given the value of RC. We are given the output. We need to find the values for R1, R2, and RE. Okay, in my example, we have chosen 1 kilo ohm and 470, so we'll roll with that. Now, on the output side, We already have the output KVL, but we need to draw the load line. So I'm going to write out the same equation from the previous slide, VCC minus VRE minus VRC minus VCE is equal to 0. I rearrange the terms, and I obtain ICRC plus IERE is equal to VCC minus VCE. Therefore, IC plus RE is equal to VCC minus VCE. To find the 2 points of the load line, if VCE is equal to 0, then IC is VCC over RC plus RE. And when IC is equal to 0, VCE is equal to VCC. In this case, for my example, IC comes out to be 8.16 milliamps, and VCE, of course, comes to be 12 volts. Those are the 2 points of my load line. Okay, those are the 2 points of my load line. Once you have the load line, you want your amplifier to work in the active region, somewhere in the center. So you want to find the point right here, somewhere in the center. Okay, this is from lab 7. This is the collector characteristics of your CE circuit. Okay, that's where this comes from. So from lab 7, the data that you have from lab 7 for your specific transistor, that's where you need to plot the load line. In this example, I'm going to choose a point that is in the center right here, 32 microamps, and my Q point is going to be an IC value of 4.3 milliamps and a VCE value of 5.8. From my graph, I can see that IB is 32 microamps, IC is 4.3 milliamps. Therefore, IE is 4.332 milliamps. Applying KVL, I have VB as VBE plus IERE. And then that gives me VB as 0.7 plus IE is 4.332 times 10 raised to minus 3 times 470. The RE for this example is 470. So I obtain VB, my base voltage, as 2.736 volts. That is also the voltage across the resistor R2. Now, IR2 can therefore be calculated as, sorry, not therefore. IR2, I'm choosing to be 10 times IB. So 0.32 milliamps. And R2, I can now calculate as VB over IR2, 2.736, 0.32 times 10 raised to minus 3 gives me 8.55 kilo ohm. For your pre-lab, of course, you'll obtain a different value. One final value remaining is R1, would be VCC minus VB over IR1. IR1, apply KCL, and you obtain IR1 is equal to IB plus IR2. You apply KCL between R1 and R2 at the base. And so you obtain 12 minus 2.736 divided by 0.352 times 10 raised to minus 3. And that gives me a value of R1 as 26.318 kilo ohms. And that is the end of your design. If you perform this calculation correctly and you design it, and your design works, you'll be in and out of the lab in like 15 to 20 minutes. Because all you have to do is you have done all the preparation in advance. All you have to do is come build the circuit with the resistors, apply input, observe the output, take a screenshot, and you're done. On the other hand, if your design doesn't work, then you'll be sitting there for 3 hours trying to figure out why it doesn't work. Okay, so extrapolate the data to go up to 15 or 16 volts. I think your lab goes up to 20 volts. So if you wish, you can do so. So you can go up to 20 volts, I would say 16 to 20 volts. And then once you have 16 to 20 volts, your VCE for IC equal to 0 would be your far right, right? And then you have your load line, intersection point. That's where you determine your Q point, obtain the IB values and the IC values as a starting point from your graph, and then perform the rest of the calculation. Lab 7 data. Okay, I will be available in my office all day until 5 p.m. Several students do come there, sit there all afternoon, work on the pre-labs, ask questions. So if you want to do that, feel free to do so. If you want to send an email, send me an email. I'll try my best to reply, answer your questions over email. All right, so we'll end class here today, and I will see you all on Wednesday.